Okay, we should be live.
Right.
So let's see. Two's complements in the computer representation of negative integers. So typically, a fixed number of bits is used to represent integers on a computer, and these are required to represent negative as well as non-negative integers. Sometimes a particular bit, normally the leftmost, is used as a sign indicator, and the remaining bits are taken to be the absolute value of the number in binary notation. The problem with this approach is that the procedures for adding the resulting numbers are somewhat complicated, and the representation of zero is not unique. A more common approach, using two's complement, makes it possible to add integers quite easily and results in a unique representation for zero. The two's complement of an integer relative to a fixed bit length is defined as follows. Given a positive integer a, the two's complement of a relative to a fixed bit length n is the n-bit binary representation of 2 to the n minus a.
I guess the image for me on YouTube is a little blurry.
Oh, is it? Let me see.
Yeah, I think it was clear. Oh no, it's good.
Let's see.
Yeah. So this is interesting. I wonder where 2 to the n minus a comes from.
Um, yeah, I have the urge to test that. Let's see. Um, Given a positive integer a, the two's complement of a relative to a fixed bit length n. So, how would you describe the two's complement?
So I guess I guess you want to represent an integer using bits, and so like each bit can have one of two states corresponding to 1 or 0. Um, and uh, so you represent the integer by representing its two's complement, and the two's complement, and so for a two's complement, like you imagine like your integer has some, you want to use some number of bits n to represent your number, um, and then given that length n, the two's complement is 2 to the n minus the number a that you're representing. Um, and so like the representation is like whatever 2 to the n a, whatever 2 to the n minus a is in binary notation.
Hmm. What is the two's complement supposed to represent?
I guess it's representing the number. Like for example, if the bit length was like 4, and then you would, instead of doing the representation of 2, you would represent 2 as 2 to the fourth minus 1, which would be 15. So I guess you would represent 2 as 15. And I guess you would do that because um I guess you would do it because that results in a unique represent. Uh,
So, like, you're saying the number one, when 4 bits are used, correlates with 15 in the two's complement?
uh, yeah, I meant to say 1. Yeah, 2 to the fourth minus 1 is 15. So yeah, 1 would be represented as whatever 15 is in binary. So it's, I guess they're kind of like shifting everything to the right, and then on the number line, like 0 is going to go to 0 is going to be represented as 2 to the n. 1 will be represented as 2 to the n minus 1. 2 will be represented as 2 to the n minus 2.
Hmm.
Um, and I guess in that case, I guess it's blurry again. Not sure why.
Let me zoom in.
Um, good. Thank you. Yeah, I guess somehow it may I guess oh yeah, I guess the thing they're gonna talk about later, how like just using the twos complement to correspond to the number makes like doing arithmetic easier. Um and it also allows for unique representation of zero. So I guess maybe what they mean there is like they said that when you're representing an like if you have like both positive and negative integers, then you need to have a bit corresponding to positive or negative on the left hand side. Um, and but zero is kind of like neither positive nor negative, or it's both. So zero wouldn't have a unique representation because you could have plus zero or minus zero. But then if you kind of shift everything to the right, then zero would just be represented as two to the n, so it would have a unique representation.
What do you mean by shift everything to the right?
It's like because like if you imagine a number line, like zero is like in the middle of the number line, but then if you're representing every number as its two's complement, then like now zero is going to be represented as 2 to the n, which is to the right of it on the number line, and like 1 is also going to be moved to the right because it's going to be represented as something a lot greater, 2 to the n minus 1. So like everything is kind of moving to it's being represented by some other number like on the right of it on the number line.
Hmm.
Yeah. Yeah, and I'm not sure why, but I guess it's kind of like it's clear for a few seconds and then it becomes blurry.
Like the let me
The
see.
text on the screen.
Interesting. So the only thing that clears the blur is what about this?
Uh, that's also blurry. Yeah, but you did something earlier that made it clear, but it lasted for a few seconds. Now it's still blurry.
Hmm.
Mm, maybe go out and back in again.
Let's see.
Maybe it's because you're zoomed in.
And is it's blurry on the stream? To me it doesn't look that blurry.
Uh, oh, looking at the YouTube.
Yeah.
Because like, let me check on a different device. 'Cause I'm watching the stream on my computer. I see on the phone.
Hmm.
Yeah, it could just be on my computer. Let's see.
When you say blurry, the character is blurry as well or just the text?
Oh, everything's blurry. Yeah, the character too.
Hmm.
Let me see. Oh, interesting. Oh, yeah, well, uh, actually, on my phone, it's not blurry. So maybe it's just my computer then. So actually, never mind. Maybe it's just some issue with my computer.
Fair enough.
Yeah,
I'm
so I'll just watch it
guessing
on the phone instead.
yeah. Hmm. For some reason when the like Wi-Fi connection isn't strong, the computer gets blurry like that. But I'm not sure if the phone gets blurry in those situations. I mean, I guess we'll see.
Yeah, it looks fine on my phone. I guess the phone can also use cellular instead of the Wi-Fi because the
True.
Wi-Fi here has been going in and out today on the computer.
Hmm.
Yeah, yeah, but this is interesting. I guess yeah, I think the later sections are going to talk about how using two's complement makes it easier to do arithmetic.
Interesting. So then would this top version be the two's complement of zero? Or am I doing this wrong?
Uh, let's see. So, well, the two's complement of zero, like whatever the bit length n is, the two's complement of zero will be 2 to the n minus 0. So the two's complement of 0 is just 2 to the n, whatever n is. Um, so like if the bit length was 4, the two's complement of 0 would be 2 to the 4th or 16.
Um, can you represent 16? You can, right? Let's see.
Yeah, and then 16 to represent that in binary. Well, 16 is 2 to the 4th power, so we'll have a 1 in the 2 to the 4th place. and then 0, 0, 0, 0.
So
Because what?
if we're using 4 bits,
Oh yeah, I guess we could 1, 0, 0, 0. Oh yeah, we don't have. Yeah, maybe. Well, huh. So I wonder what we do then, because like we can't represent that with just 4 bits. Yeah, that's a bit tricky.
so okay, the
Oh well, wait,
formula.
oh no, but yeah, well, yeah, I wonder why they do it that way then, because you can't do that with 4 bits.
Well, maybe it works with a different number. So like
Yeah.
with 1, you should get.
Oh wait, actually, it says given a positive integer a, so you can only do the 2's complement for a positive integer, not for 0.
So if we use 1 instead, then we get 16 minus 1 to get 15, right?
Yeah. Oh yeah, and that can be done with 4 bits. Oh yeah, so maybe there's like some reason like you can't do it for 0, but you can do it for 1, and yeah, you can do it
Interesting.
for 1 and like anything up to 2 to the n probably.
So that makes sense.
Yeah. Oh yeah, I missed that. So it has to be a positive integer. Yeah, and then 15, that would be like, so it's like 8 plus 4 plus 3, 8 plus 4 plus 2 plus 1. So that's going to be like 2 cubed plus 2 squared plus 2 to the first plus 2 to the 0. So it'll be 1, 1, 1, 1.
Makes sense. So let's see. The 2's complement of 1 is 15. So the 2's complement of 2 is likely 14 because we didn't change the bits, right?
Yeah.
Um, right. The 2's complement for 3 would be 13.
Yeah.
So with 5 bits, let's see would the 2's complement change? I guess it would, because it seems like we're subtracting the total, like the greatest number possible with that given amount of bits. We're
Yeah.
subtracting that like greatest, uh, or we're subtracting the number from that greatest magnitude, and then whatever the result is the 2's complement. So I guess if you use the greatest number possible in the formula, you think you would get 0?
Yeah, it would. Like if you wanted to find, like if you had 5 bits and you want to find the 2's complement of 2 to the 5th or 32, then you'd have 2 to the 5th minus 2 to the 5th, so you'd have 0. So you just do 0, 0, 0, 0, 0 with 5 bits.
Hmm.
Yeah, and that's interesting because I guess like smaller numbers have bigger 2's complements because
Right.
you're subtracting the number from 2 to the n.
Right. Hmm. So to get 0, but you can't represent 16 with 4 bits, right?
Uh, 16. Yeah, you can't represent it with 4 bits, so you'd have to have 5 bits. You could find the 2's complement of 16 with 5 bits, then that would be 2 to the 5th minus 16.
Hmm. So the 2's complement of 15, which is when all the bits are on, is 1.
Yeah,
Okay. So we figured out the 2's complement is you take the number you subtracted from 2 to the n.
yeah,
Um, but I guess you I wonder if you can use to the n. You can plug it into the formula, but you can't represent it with bits. So I wonder if the chapter explains what to do for like trying to plug 2 to the n into this formula.
Yeah. Well, I guess you can do the 2's complement of 2 to the n. Like, I guess if you have n bits, it would be 2 to the n minus 2 to the n. So the 2's complement of 2 to the n
Would be
would be 0.
true, but how would you represent to the n with bits?
Oh, uh, well, I guess if you're representing it, like, I guess was this method, with this method, like, you represent it as whatever its 2's complement would be. So you would represent 2 to the n as 0, and then you would have, like, if you had 5 bits, then that would be 0, 0, 0, 0, 0.
Well, let me see. If you had 5 bits, hmm,
Because you can, you can add more, as many zeros at the beginning as you want.
right?
So, like, you could represent 0 as 0. You could also represent it as 0, 0, or 0, 0, 0, depending on how many bits you have.
Yeah, I mean, I guess the formula's not broken. You can get the 2's complement of, um, I guess, of any number.
Yeah. Yeah, and I guess, like, if you have n bits, you can get, like, anything from 1 to 2 to the n. You can take the 2's complement.
And I guess it doesn't seem to correlate with how many, with what numbers you can actually express with the number of bits you plug into the formula. Like, there's no correlation between like the integrity of this um, representation of bits that I'm pointing to and the formula, because in this representation of bits, um, you can't represent 16, but I guess the formula doesn't care about that. Like, you can put 2 to the 4 minus 16 into the formula and it gets you, a result. It might be entirely unrelated to the limitations of what you can actually represent with 4 bits.
Yeah. Yeah. Well, yeah, if you plug in 16, you have 2 to the 4 minus 16, so you have 0. And, like, yeah, normally you can't represent 16 with 4 bits, but I guess with a 2's complement, you can.
With a 2's complement, you can, or just like with just this linear algebra, this like algebraic representation allows you to represent all numbers. Um,
Yeah. Yeah, as long as you have enough bits.
Even
Because,
if you don't, like you can even plug in 17 into the 2's complement and you'd still get a number.
yeah.
The formula
Yeah,
is
you see, we get,
simple.
yeah, you would get -1, I guess. I guess if there's, I guess,
That's
yeah, I mean, I guess if you have, like, a bit to represent the negative, then you can have, like, negative, and then and then 0, 0, 0, 0, 1.
interesting. But eventually you'd be unable to express it with the bits, wouldn't you? Like, you would have the same combination of bits representing multiple different numbers. Like, let's see. If you plugged in 200 into the formula instead of 17 with 4 bits,
Yeah, then you couldn't do it. You wouldn't have enough bits. So, yeah, like, I think it's like the bit size that you choose depends on, like, what numbers you want to represent. Like, if you were representing, like, a really, like, 200, then you need to have, like, a bit size that allows for that. Um, so it's like if you have n bits, then using the 2's complement, I think you can represent it, like, any positive integer from 1 to 2 to the n. And maybe, like, a few more if you also can also do negatives.
yeah, you said you could represent anything from 1 to 2 to the n.
Yeah, because you can represent like well, you can represent 1 because that would be 2 to the n minus 1. And then you just keep going, and once you get to 2 to the n, you'll have the representation of 2 to the n be 0. Um, so that's going to cover all of the possibilities that you can represent with n bits.
Hmm.
Like for example, for if you have 4 bits, the representation of 1 would be the whatever the binary representation of 15 is. Then 2 would correspond to 14, 3 would correspond to 13, etc.
See.
Until you ultimately get to like 15 would correspond to 1, and then 16 itself would correspond to 0.
That's
So
cool.
with yeah, with like 4, 2 to the n, if n is 4, 2 to the n is 16, and you can represent anything from 1 to 16 with the 2's complement.
Ah.
Yeah, I think they didn't explicitly say that, but I think that's the case.
Yeah. Fair enough. Let's see. Bit lengths of 16 and 32 are the most commonly used in practice. However, because the principles are the same for all bit lengths, we use a bit length of 8 for simplicity in this discussion. For instance, because...
And the subscript 10 is indicating that those are being written in decimal.
Yeah. 2 to the 8. What was the easy way of calculating this?
Well, I guess one way is to kind of just go through it, like that 2 to the 4th is 16, 2 times that is 32, 2 times that is 64, 2 times that is 128, 2 times that is 256.
Ah,
Um, yeah, so could memorize it, or could like kind of start from one that you know and then keep multiplying by 2 until you get there.
interesting. Oh, let's see.
Yeah, so here we have a bit length of 8, and we're finding the 2's complement of 27. So that's 2 to the n minus 27, so 2 to the 8th minus 27. And then
Right.
calculating that is 229. And then they like wrote what 229 as the sum of powers of 2 to figure out the binary representation. And then that binary representation would be the 2's complement.
Right. Hmm. It turns out that there's a convenient way to compute 2's complement that involves less arithmetic than direct application of the definition. For an 8-bit representation, it is based on 3 facts. Um, 2 to the 8 minus a equals 2 to the 8 minus 1 minus a plus 1. The binary representation of 2 to the 8 is 1, or minus 1 is 8 ones. Subtracting an 8-bit binary number a from 8 ones just switches all the zeros in a to ones and all the ones to zeros. The resulting number is called the ones complement of the given number. For instance, by 2 and 3 with a equals 27.
So let's see. Yeah, maybe it's worth discussing those rules, those observations. So I guess they're kind of like coming up with like a shortcut for doing arithmetic.
Really?
Yeah. Um, or oh yeah, I guess they're like coming up with a shortcut for finding the 8-bit two's complement. And like to kind of prove that the shortcut works. Oh yeah, and the shortcut would be that thing in the box. Like so like mechanically, if you're finding the 8-bit two's complement for a positive integer, up to 255, and 255 is 1 less than 2 to the 8th, then you write the binary representation for that integer, then you switch all the ones to zeros and the zeros to ones, and then you add 1 in binary notation. And that's the mechanical procedure for finding the two's complement. And then the stuff above is explaining why that procedure works.
That is a nice procedure. I'm just
Yeah, let's look at the reasoning behind it again. So if we want to calculate the 8-bit two's complement, oh yeah, and that's I think it's at the top of the next page.
oh, I'm there was some language in here.
Yeah, the blue box up there. Yeah, that one. At the top of page 85.
it's just this paragraph kind of like piqued my curiosity here. Let me
Oh
read
yeah.
these words. Turns out that there's a convenient way to compute two's complement that involves less arithmetic, right, than the direct application of the definition. Okay, for an 8-bit representation, it is based on 3 facts. I wonder, what does that mean? Because I get the procedure, which is that you use the ones complement and then you add 1. So
Yeah.
where do these 3 facts come in? Like, why is it important to know these?
I think the 3 facts are just kind of prove that the procedure works.
Prove? How do you? Or I mean, like, what does that mean? Isn't a procedure just a sequence of steps? Like, what do you mean by
Yeah,
works? Or what is? Yeah, how do you define
meaning that
works?
like it works in the sense that if you apply it, you do in fact get the two's complement. Because like this is like showing that like this really does give you the
Oh,
two's complement. Like yeah, so like in the blue box further down, like there's a series of steps, and then like these 3 facts are the reason why those steps give you the two's complement.
interesting.
Yeah. Yeah, so the first thing they say is like, well, when we're trying to find the two's complement, since we have 8 bits, that means we're trying to find 2 to the 8th minus a. And the first thing they observe is that 2 to the 8th minus a equals 2 to the 8th minus 1 minus a plus 1. And the reason for that is that, like, well, 2 to the 8th minus 1 minus a plus 1, if you just rearrange, then that's 2 to the 8th minus a minus 1 plus 1. So minus 1 plus 1 that's just like adding 0. So they kind of
Okay.
just rewrote it in a convenient form. Yeah. So that's the first step. Like they just put in a minus 1, and they also put in a plus 1, which they're allowed to do because subtracting 1 and adding 1 is the same as adding 0. So it doesn't change the value.
Is there anything
Um,
important about these parentheses that they're using? Is that the magic here?
uh, I think it's gonna reflect. Yeah, it's gonna reflect like the steps of the procedure, because in the procedure we're gonna start with 2 to the 8th minus 1, then we're gonna subtract a, then we're gonna
Oh,
add 1. So the parentheses are kind of reflecting the order that we're gonna do things.
fair enough.
Yeah, and then they say like, okay, so let's start by figuring out what is 2 to the 8th minus 1 in binary representation, and it happens that that's 8 ones. Um, And so they got that. And so now, like, to figure out the 2's complement of A, we can take those 8 ones, then we subtract A, and then we add 1. So subtracting A from that binary number that's 8 ones, that's gonna switch all the zeros to ones and all the ones to zeros. And then, like, why is that? So that would be because, like, well, like, if you have when you're doing the subtraction, you'll go column by column. So if you have like the 8 ones and then you subtract A, if A has if it has a 1 in a given column, then in that column you're going to have 1 minus 1, which is 0. And if you have a 0 in the column for A, then that's going to be 1 minus 0, which will be 1. So that will be why subtracting 2 to the 8th minus 1, or ordering 2 to the 8th minus 1 minus A would switch all the ones to zeros and the zeros to ones.
Mm.
Yeah. So so that's what we're doing when we're switching all the ones to zeros and zeros to ones. We're taking what we're really doing is taking 2 to the 8th minus 1 and subtracting A from it.
But
And then
as
the
long
last
as
thing we
A is all ones. Oh, wait,
uh
subtracting A from all ones, actually.
yeah. Yeah, so the idea is what if so you're doing one you have the 8 ones on top and then you have A on the bottom, and you're doing like the 8 ones minus A. And then when you do the subtraction, you go column by column. So you look at in each column, in the top, you're going to have a 1. And in the bottom, you're going to have whatever A has in that column. So, suppose A has a 1 in that column. You're always going to have a 1 on top, and then you have a 1 on the bottom. So 1 minus 1 is 0. Um, so you're going to have a 0 in that column for the result. And then suppose you've got a 0 for A in that column, then you always have a 1 on top because the thing on top is all ones. So you're going to have 1 minus, yeah, it's good to illustrate it.
Yeah, I just
Yeah,
noticed it's gonna change. It says it's going to switch all the bits in A, right?
yeah, and A, exactly.
Okay.
Yeah, yeah, and that's how it works. Is you like 1 minus 1 is 0, so it switches ones to zeros, and 1 minus 0 is 1, so it switches zeros to ones. Yeah,
Hmm.
yeah, so that's why we do that first step, switching all the ones to zeros and the zeros to ones. And then the last thing we got to do is just add 1. So that's why the procedure works to give us the 2's complement. The procedure being that we just need to write the binary representation for A. Then in that we switch all the ones to zeros and all the zeros to ones. And then we add 1.
Hmm.
Yeah, and adding 1 is relatively straightforward because 1 is just 0, 0, 0, 0, 0, 0, 1, or 7 zeros and then 1.
So what happens if A is 0?
Uh, I guess by definition we can't let A be 0 because the 2's complement is only defined for a positive integer.
True. And then if A equals 2 to the n,
Yeah, I guess they're not letting it be 2 to the n either, it turns out, because in this case 2 to the n would be 2 to the 8th, which is 256. But here, like in the procedure, they say we can only go up to 255.
and
Um,
oh, does it?
yeah, which I'm not sure why, because I guess the 2's complement of 256 would just be 0, it seems. But
Hmm. Where does it
oh,
say?
I guess because actually 256, we can't apply the procedure to 256 because we can't write the representation of 256 using only 8 bits. We need 9 bits.
Right.
Yeah. So I guess it's like we can do the procedure for numbers from 1 to 255. And those are the positive integers that you can write using 8 bits. And then we'll write them using 8 bits, switch the ones to zeros and the zeros to ones, and then add 1.
Hmm. It's just weird that in the definition, I guess it specifies that zero can't be used. The two's complement is not defined for zero,
Yeah.
but it's not specified that the two's complement's not defined for two to the n. Right?
Yeah. Yeah, it's not. And I guess the reason I think it should be defined. Like I think it probably is defined for two to the n because like it would just be zero. But the thing is that like in the blue box further down, that particular procedure just happens not as described. It doesn't work for two to the n because 2 to the n is 256. And then the first step it says write the 8-bit binary representation for A, but 256 would have a 9-bit binary representation.
Right.
Yeah, but I guess you still could technically calculate the two's complement for 256, I think, because it would just be 256 minus 256, and that would be 0, and then you just have 8 zeros. But I
Right.
guess, the way they're formulating the procedure, like, it's just for 8-bit things.
Yeah. Interesting. So you think the two's complement is a concept that is just being applied to the 8-bit world, but it's, not an 8-bit concept per se?
Yeah, you could do it like you could pick any n you want for the two's complement. You could do the 16-bit two's complement or the 157-bit two's complement.
Yeah.
And I guess they're just doing it with 8 because it's a relative like it's not too big of a number and it's just like to illustrate the principles.
Hmm. Let's see. Finding a two's complement. Find the 8-bit two's complement of 19.
Yeah. Yeah, so now we can apply the procedure.
So first we'd need to, wouldn't we need a representation of 19, an 8-bit representation?
Yeah.
So what do we have?
Yeah, so we got to find the biggest power of 2 that's less than or equal to 19. Yeah.
Like,
And then we have 3 left and then so we'll
um,
have 16 plus
plus 3.
yeah, 16 plus 3, and then 3 would be 2 plus 1.
So the one one's complement would be
Yeah. Oh,
this.
yeah, just one more thing, though, because here we have 6-bit. We have 100 110, so that's 6 bits there. So we need to add 2 zeros at the beginning to make it 8 bits.
Ah, true.
So before the 1 zeros, yeah, exactly.
I wonder what this is used for. They say it's typically used in 16 and 32-bit situations.
Yeah. Yeah, and I guess maybe that's like because computers could work with relatively big numbers, so maybe they could work with numbers like as big as 2 to the 16th or 2 to the 32nd. So it's kind of like depending on how much data you want to look at in a particular context.
And I wonder why using the two's complement would be superior to just using, like, without doing this procedure to your A.
Yeah, I don't know. I guess somehow it's like more convenient for representing it. I guess maybe like the computer can just do this procedure and maybe it's like simpler and takes less energy than doing regular arithmetic.
Hmm. Yeah, maybe it'll tell us somewhere in the summary or something. I'm not sure if it'll tell. See.
Yeah. Yeah, I'm not sure. Yeah. But yeah, I guess now we gotta add 1 to that thing with the bits flipped. Um
Right. I, I guess they want the two's complement in decimal.
oh yeah, I guess yeah, just to double check, I guess. Yeah, and then when we're adding one, we just like we'll have one is just going to be a one, like 7 zeros followed by a one. So like you'll have 0 plus 1. Yeah,
Yeah.
yeah.
So we have, let's see. So where did I make a mistake here?
Oh yeah, I think you add an extra zero at the end because you have the 16's place, the 8's place, the 4's place, the 2's place, the 1's place, but there isn't a zero's place.
You mean here?
Like like in the part where you have 16, 8, 4, 2. Yeah, so the last zero, I'm gonna omit that one because there isn't a zero's place. It just goes to the one's place.
Ah. So didn't you say, oh, the ones place? This was actually supposed to be my what do you call this? Mm, K here, the exponent.
Yeah. Oh yeah. Oh, so in that case, then the everything would be shifted a little bit because like the twos play like um yeah. So but like the numbers you have there are like two raised to different powers. So like 64 is two to the um
Ah.
yeah, 2 to the sixth, and then 32 is 2 to the fifth, 16 2 to the fourth, 8 2 cubed, 4 2 squared. 2 is 2 to the first, and 1 is 2 to the zero. So the zero column would just go away.
What do you mean by the zero column would go away though? Because this
Uh
would be the
oh
yeah, this would be two to the zero, which could be
oh
one, right?
oh, but the thing is that like we don't have a zero. If that's the exponent, we don't have a zero in the 2 to the zero place. We have a 1 because like um we had that 16 equal or sorry 19 equals 16 plus 2 plus 1, so we should have a 1 in the 2 to the zero place. And
Oh, let me see.
because we have like 19 equals 2 equals 1 times 2 to the fourth plus 1 times 2 to the first plus 1 times 2 to the zero.
Wait, say this one more time. Or
So we had I think everything is just shifted to the right by 1 because we had 19 equals 1 times 2 to the fourth. So the first one actually goes on the 4 column. Um, yeah, 1 times 2 to the
ah,
fourth plus 1 times 2 to the first plus 1 times 2 to the zero. 16 plus 2 plus 1.
I wanted to
Yeah,
have that map too. But let's see. So you said
yeah. So we'll have a 1 in the 2 to the fourth place, and then a 1 in the 2 to the 1 place, and a 1 in the 2 to the zero place, and then zeros everywhere else. Yeah. Yeah, and then we'll flip the bits so it'll become yeah, and then we add one. So adding one, that's like one in the 8-bit binary representation would be just like 7 zeros followed by one.
see.
So yeah,
And the answer they arrived with is this.
yeah, Yeah, and then they just double check to make sure, and that does turn out to be right.
I see, I see. Hmm.
Yeah, and now they're going to talk about going in the reverse direction. Like, if you're given the 2's complement, find the number in decimal notation.
Ooh.
Yeah, I guess I can read that part. So observe that. Um, oh, yeah, I can also do the top of the page we haven't read yet. Yeah,
I see.
yeah. So observe that 2 to the 8th minus 2 to the 8th minus a equals a. So the 2's complement of the 2's complement of a number is the number itself. Um, and that's because like 2 to the 8th minus 2 to the 8th minus a, so that's 2 to the 8th minus 2 to the 8th minus a is plus a. So you have 2 to the 8th minus 2 to the 8th is 0, plus a is a. And here you're like taking 2 to the 8th minus 2 to the 8th minus a, and 2 to the 8th minus something is the 8-bit 2's complement. So we're taking the 2's complement of the 2's complement. So since the 2's complement of the 2's complement is the number itself, to find the decimal representation of the integer with the given 8-bit 2's complement, find the 2's complement of the given 2's complement, and write the decimal equivalent of the result. Oh, that's clever. So so the problem is like you're given the 2's complement of something in binary notation, and you want to find what was it in decimal notation. And to do that, like you first take the 2's complement of the 2's complement, and that brings you back to the original number. Um, and then you find the decimal representation, and that'll be the decimal representation of the original number.
Interesting. The 2's complement of a number. Whenever you like say the 2's complement of a number, isn't the 2's complement a function with two inputs, like the bit length as well as the number?
Yeah, it is. So here they're kind of like assuming that the bit length is 8. But yeah, you're right that like in general, they need to specify what the bit length is as well as what the number is.
Interesting. I feel like I've always heard the 2's complement used, but very rarely have I heard it have both of its inputs specified. It's always, oh yeah, find the 2's complement of X. But yeah, clearly it has two inputs.
Yeah, yeah, it does. Yeah, like the 2's complement relative to a given bit's length.
Right. So the 2's complement of the 2's complement of a number is the number itself. I guess
Yeah,
that means for all bit lengths, right?
yeah, yeah. So that would be true if you were doing like the 16-bit 2's complement, because like 2 to the 16th minus 2 to the 16th minus a equals a.
So let's see. 2 to the 16th 2's complement for 1. Or maybe there's like an easier one. I think 2 to the 8, they said, was
Yeah,
a pretty easy one. So
yeah, they're just working with 2 to the 8. Yeah.
if we plug in 1 for A, first off, what's 2 to the complement? What's the 2's complement of 1 when the bits are 8? And then we'll see if finding the 2's complement of that number gets us back to 1. I guess I can already see that it probably would.
Yeah, it can actually be seen algebraically without even plugging in 1, because like 2 to the 8th minus 2 to the 8th minus a. Well, if you subtract 2 to the 8th minus a, that's the same as
Ah,
like 2 to the 8th minus 2 to the 8th plus a, because like you take the negative of everything inside the parentheses.
right.
Yeah, so you have 2 to the 8th minus 2 to the 8th, that's 0, plus a is a.
Right.
Yeah, so that guarantees that that's always gonna be the case for any a.
Hmm. I have a small urge to put like under the microscope why it goes back to the original number. I think
Yeah,
it has something to do with the procedure, but it like
yeah,
apparently loops perfectly back onto itself, right?
yeah. Oh, yeah, why it works, like, I guess yeah, well, I think it works, maybe it just works because of that algebraic fact, because the two's complement is by definition 2 to the n minus a, so the two's complement of that is by definition 2 to the n minus 2 to the n minus a, and then
Right.
algebraically, like, 2 to the n minus 2 to the n minus a is 2 to the n minus 2 to the n plus a, which is a.
But like how certainly can we rely on the algebraic perfection here when our 8-bit representation is limited in ways that the algebra is not? Like, how can we rely on the perfection of the algebra to describe how the 8-bit representation will behave? I guess in this case it does, but it might just be coincidental.
Yeah. Oh, yeah, that's a good point, yeah, compliments to you for that,
Hilarious.
yeah. Yeah. Yeah, so let's think about that. I guess I guess that well, like what could the potential problem could be that like we end up with something that can't be represented with 8 bits. So like let's see if that could happen. Well,
Right.
yeah. So we're taking the two's complement of 2 to the 8th minus a, and like can 2 to the 8th minus a be represented with 8 bits? Um, I guess, well, we're assuming that a is something from 1 to 255, and like we already know, I guess, that like anything from 1 to 255 has an 8-bit two's complement. So like we're gonna have something that's representable with 8 bits for 2 to the 8th minus a.
Because the 2
And
to the complement, I guess, function, it always returns a number that's within those bounds as well, right?
yeah, yeah, it does. And then like we have something that's 8 bits already, and then we're taking the two's complement of it, and then that's also going to give us something with 8 bits because the procedure is just flipping the bits and adding 1.
So the procedure never produces a 0 because 2 to the n is not an input we're allowing, right?
Yeah,
Okay. Those like those boundary um I don't know what you call them. Those boundary values are like mapped together. So as long as you don't use them, you don't get the other boundary. As long
yeah,
as yeah, as long as you don't put a boundary in the input, you don't get a boundary in the output.
yeah,
Okay, that's cool. So because of that two's complement symmetry, you can use it on itself to get the original number.
yeah.
So what was the point of doing this again? To find the decimal representation of
Yeah, so the goal is like, so we already saw like given a number in decimal
oh,
notation, how can we get the two's complement? And that was like, what if we want to go in the reverse direction? And then to go in the reverse direction, like we're given a two's complement in binary notation. So we find the two's complement of the two's complement, and that gives us the binary representation of the original number. Um, and then we can write that in decimal notation, and then we have the decimal notation of the original number.
okay. So what's the Right. We don't have the original number originally. We just have
Yeah,
its two's complement.
yeah.
So, yeah, flip the bits and add one. And then it says find the. This part is giving me so much trouble finding the decimal representation of a binary number.
Oh yeah. Well, what we can do is like look at like what does binary representation mean? And it means like so like ones and zeros times powers of two. So like the power of the rightmost power of two is one. So we're gonna have that's why we have one times one to the right, which is one. Um, and then the power to the left of that is two to the first, which is two. We have a one there, so we get a two in the sum. And then to the left of that, the third to the far right, and that's going to be the next power of two, two squared, which is four. So we get a four in the sum. And then the next power of two, two cubed, we get have zero, so we don't so nothing in the sum there. Then the next spot we have a one, and that's the two to the fourth spot. That's 16, so we'll have a 16 in the sum. Then the next spot we have zero, so nothing there in the sum. And then the next spot we have one, that's the two to the sixth power, so which is 64. So we have a 64 in the sum. So the idea is like what 0 1 0 1 0 1 1 1 means is 0 times 2 to the seventh plus 1 times 2 to the sixth plus 0 times 2 to the fifth plus 1 times 2 to the fourth plus 0 times 2 to the third plus 1 times 2 to the second plus 1 times 2 to the 1 plus 1 times 2 to the 0.
Right. It seems like the amount of work that you have to do each time you want to really calculate the decimal representation of a binary number is you need to first map the exponent to, like a decimal number. Or maybe they consider exponents decimal numbers as well. What do you call the
Yeah, yeah.
transformation between the exponential type and like the I don't know, the flat number?
Yeah, yeah, it's kind of like you gotta like look at how many digits there are and like each place, like what power of two does it correspond to?
Right. So you need to do that mapping, and then you also need to sum all of that, all those maps together.
Yeah.
Because to add, and do you know the name for this form? Like where you have the exponent? Is it
Uh,
exponential? No, no. I think it had an actual name
uh, I guess
for.
a power of two.
Well, when you're adding powers,
Oh yeah.
I guess you have to. What do you call it whenever you? Is there a word for the verb of like
Like adding the powers of something.
if we call these powers, then what do we call it when they're not in this power form? Like, what do you call 16? Relative
Uh,
to powers. 16
oh.
would not be. I mean, yeah,
I mean, I guess you could say 16 is a power of 2 in the sense that 16 is 2 to the power of some integer. Because I guess it is equal to a power of 2, so you could kind of say it is a power of 2.
a power of two.
Yeah, like 4 is a power of 2, even if you don't explicitly write it as such.
Interesting, but then we'd still need a name for something that is not written as a power. Or maybe I'm describing that a little wrong, but like obviously these two forms are different but equal.
Yeah. Yeah, and I don't know if there is like there are separate names for them. I mean, I guess you could say like 2 raised to a power, and that makes explicit that you actually have an exponent being written.
Right.
Um,
But
yeah, so that could be.
if I wanted to talk about multiple ones, how would you talk about multiple ones?
Yeah. Yeah, I think I don't think there is a term for it, at least that I know of. I guess you kind of just have two powers of two, and powers of two could refer to two to the first, two squared, two cubed, or you could just say that there are two, four, 8, 16. Um, yeah, I'm not sure if there are separate names for them.
Well, I mean, powers is a good enough name because that lets you do multiple. If we called each one of these forms a power,
Yeah.
that gets the job done. But then we need a name for the other one, the one that's not
Yeah.
a power. I mean, it is a power in one sense, but the point of this name is to differentiate between what it is and like what we really need with powers.
Yeah. I guess. Yeah. I don't know if I don't. Yeah, there should be a name, but I think there isn't. There isn't, as far as I've heard. I haven't seen one. I guess. I guess. Yeah. Maybe as the idea is that like they're just two different ways of writing the same thing, and I guess maybe they don't have an explicit name for that way of writing it, where you actually explicitly write the exponent, other than two raised to a power, I guess. But
Raised to a power. Yeah, two raised to a power.
yeah, so you could say like there are multiple twos raised to powers, I guess. Oh, it's kind of a clunky thing to say, but
Right, because technically you're not adding powers. You're,
yeah,
you're
yeah.
adding
Although
two raised to the power. You're adding two raised to various powers.
yeah, although I think power can be kind of ambiguous because maybe it can sometimes be used to refer to the exponent, sometimes refer to
Exactly.
like yeah, like let me
Oh,
double check like powers of two. Um,
interesting. Maybe powers is an okay word then.
yeah, yeah, because like yeah, I was double checking like yeah, that's like the powers of two are one, two, four, eight. So powers of two can refer to like just
The
yeah, one, two,
number.
four, eight, 16. But you can also say like two raised to the power of four. In that case, power refers to the exponent. So I guess power can kind of be used in kind of different ways.
Interesting. But would really it'd be nice to have names for these forms.
Yeah, yeah, it would be nice. Maybe there are names that I just haven't heard.
16 would be on one hand 2 raised to the power of 4, or I guess it could be 16 to the power of 1. So I suppose I would need a name for all of the like all numbers raised to the power of 1.
Yeah,
I mean, I guess integers
yeah,
isn't a proper word because that also encompasses the powers. So I need a word that refers to the powers of, well, refers to numbers raised to the power of 1 that doesn't encompass numbers raised to the power of anything other than 1.
yeah, yeah. I'm not sure they, because I mean, like just plain integers and covers all of them, but
Right.
they're not conceptualized as being raised to the power of one. Like they have it for the
Right.
power of two and the power of three. Like the power of two, those would be squares, or perfect squares, and then the power,
Right.
yeah, power of three you have cubes, but
Indeed.
yeah, but you don't have it for the power of one.
Huh.
Yeah, so I guess if there were like a math convention, I'd have to like raise an objection to the lack of a term for that.
Right. Hmm.
Yeah,
Well, let's see. Yeah, what I was saying is so far it seems like the best way we have of um, translating from a binary representation to a decimal representation is first we would have to identify the number raised to the power of 1 for each of the bits that's a 1.
yeah. Or well, I guess like well, so we're given like two's complement, and to find the original number, we got to find the two's complement of the two's complement. So what we'll be doing is like, well, we flip the bits, then we add
Right.
one, then we have the two's complement, or no, then we have the binary representation of the original number, and then we to figure out what that is in decimal notation, we've got to like just go through and like add all of the powers of two that have a one in the corresponding spot.
Right. And going through and adding all of the numbers that have a power of 1 is actually two like sizable chunks of calculation unless you memorize what all of the powers of 2 equate to. If you don't, then you have to calculate each of these powers of two eh, again and again,
Yeah.
and then you sum them together, which is also like kind of intensive. You can either try and do it in your head or write it out, but it's like a hefty calculation. To do 50 of these would be quite a lot of work if you don't have it memorized. That mapping section.
Yeah. Yeah, and by the way, every time you said like two there, we have to calculate this. Every one of those
Oh,
twos was a pun. Yeah,
hilarious.
yeah, yeah. But yeah, I guess yeah, it would be you have to do a calculation there. Yeah, because there isn't like a shortcut algorithm for it.
Yeah, I imagine doing it like hundreds of times, it could become quite easy because you're adding the same numbers over and over again. So, in a way, you can kind of memorize the additions as well. It's a lot more additions if you're dealing with, let's see, like if you're dealing with 4 bits, would it be the number of possible additions you can make? I wonder how many that would be because each bit can be added with one other bit as well as with two other bits and with three other bits or with none.
Mm.
I'm pretty sure this type of possibility math is covered in a later section, so I'm not. But would you have a guess at to how many possible additions you could get with 4 bits?
4 bits. Well,
Oh,
yeah, I guess yeah, because I guess you with 4 bits there are 16 possible combinations of bits. Because like each bit you have four of them, and each one can be either 0 or 1. And to find the total number of possibilities, that would be like you have two possibilities for the
right,
first one, yeah, then two for the second, then two for the third, then two for the fourth. So it's two times two times two times two, which is 16. So if you have a yeah, if you have 4 bits, then you have two to the fourth uh, possible combinations of bits, which means you have two to the fourth possible like additions to do to calculate the decimal representation.
right,
Yeah, and yeah, I think it might come up in a later chapter, like counting the number of possible ways something can happen.
right. Um,
There's actually a whole area of math about that, like counting the ways something can happen. It's called combinatorics.
right. That's what I suspect is later on in the book.
Yeah.
But now let's see. In any case, so suppose it'll always be the number of bits. Um, well, it would be 2 raised to the length of the bits, right?
Yeah, yeah, it would. Yeah, that would be all the possible combinations. I guess all the possible numbers that could be represented with that many bits.
Hmm. So if it were 8 bits, and I like to think that humans are probably only calculating it by hand up to 8 bits, maybe 16. I don't know, but let's see. So with 8 bits, this gets us, isn't this 256?
8 bits, yeah, 256. So we have 256 possibilities for what we could represent with 8 bits. And in
Interesting.
fact, I guess we could represent any number from 0 to 255 using 8 bits.
Right. So, like, I think calculators are now strapped with the ability to type in the exponent as well as the base number, right?
Yeah.
Okay. So you always have the map on hand. I mean, you have to type in the exponent and the base number for each of the digits, but at the very least, you do have that, or you could just have a map. I guess in terms of memorizing, you would only have to memorize 32 positions.
Yeah.
So that would reduce a lot of the work down to just adding. Um, hmm.
Yeah. Yeah. I guess. Yeah, you could. I mean, I guess you would have to think about like. I mean, I guess it depends how much you're doing it. Like maybe because if you're only doing this kind of calculation a little bit, it might be faster to just do the calculate. Like it might take less time to just do the calculation
True.
when you've got to do it than it would take to memorize all the possibilities. But I guess if you're doing the calculations like all the time, maybe at a certain point, memorizing them would save time. Um,
Yeah.
yeah, it's kind of like if you're using powers of two a lot, then it could be save time to memorize them up to a certain point.
Yeah.
Yeah. But yeah, I wonder where they're going next here. Let's see. Um, yeah, I guess I can read this one. So we got a 8-bit representation of a number. Now consider the two's complement of an integer n that satisfies the inequality 1 is less than or equal to n is less than or equal to 128. Then -1 is greater than or equal to -n is greater than or equal to -128 because multiplying by -1 reverses the direction of the inequality. And so now they're adding 2 to the 8th to every part here. 2 to the 8th minus 1 is greater than or equal to 2 to the 8th minus n is greater than or equal to 2 to the 8th minus 128 by adding 2 to the 8th to all parts of the inequality. But 2 to the 8th minus 128 equals 256 minus 128, which equals 128, which equals 2 to the 7th. Hence, 2 to the 7th is less than or equal to the 2's complement of n, which is less than 2 to the 8th. And that's because they're kind of flipping the inequality around. Like we had the 2's like yeah, they're kind of just like writing it the reverse way. 2 to the 8th minus 128 they showed was 2 to the 7th. And the 2's complement of n, 2 to the 8th minus n, is greater than or equal to 2 to the 7th. So 2 to the 7th is less than or equal to the 2's complement of 2 to the n of n. And the 2's complement of n, 2 to the 8th minus n, is less than or equal to 2 to the 8th minus 1. Which means that it's less than 2 to the 8th because like if it's already less than or equal to 2 to the 8th minus 1, 2 to the 8th is bigger than 2 to the 8th minus 1, so it's got to just be less than 2 to the 8th. So, and it follows that the 8-bit 2's complement of an integer from 1 through 128 has a leading bit of 1. Let's see what that means. Oh, okay. So because so 2 to the 7th, that's going to be in binary notation, that's going to be 1 followed by 7 zeros because you're going to have a 1 in the 2 to the 7th place and zeros everywhere else. And then everything like everything greater than that that still can be represented with 8 bits, that's going to be like 2 to the 7th plus some other powers of 2. So you'll still have that 1 in the 2 to the 7th place. Once you get to 2 to the 8th, then you'll no longer have the 1 in the 2 to the 7th place, but you won't be dealing with things that can be represented with 8 bits anymore. So the 8-bit 2's complement of an integer from 1 through 128 has a leading bit of 1. Note also that the ordinary 8-bit representation of an integer from 0 through 127 has a leading bit of 0. meaning that there's a 0 in the 2 to the 7th place, because all of those are numbers that are less than 128, less than 2 to the 7th. Consequently, 8 bits can be used to represent both non-negative and negative integers by representing each non-negative integer up through 127 using ordinary 8-bit binary notation, and representing each negative integer from -1 through -128 as the 2's complement of its absolute value. That is, for any integer a from -128 through 127, the 8-bit representation of a equals the 1-bit binary representation of a if a is greater than or equal to 0, the 8-bit binary representation of 2 to the 8th minus the absolute value of a if a is less than 0, and then there's a table that lists them. So that's worth discussing. Let's see. Yeah, so they have integers together with what their 8-bit representations would be. So I guess the idea is like what we were doing before. We were able to represent any number from, or like in general, like forgetting about 2's complements, we're able to represent, like if we're just using ordinary binary notation, we would be able to represent any number from 0 to 255 using just 8 bits. Because 256, that's when we'd have to start using 9 bits, because we'd have 1 followed by 8 zeros. So ordinarily, we could represent anything from 0 to 255 using just 8 bits. But now they're saying like, well, like what if you want to represent negative integers as well? And like you want each number to have a unique representation. Like you don't want it to like 2 binary representations to correspond to different things. Or sorry, you don't want 2 numbers to correspond to the same binary representation. So like they're saying, let's split up. Let's like the numbers from 0 to 128. We'll just represent those. Oh no, 0 through 127. We'll just represent those normally. They're not including 128. Let's see.
I guess because the positive integers are restricted to the 7 bits.
Oh yeah. Oh yeah. They have to have the leading 0 at the beginning. Oh, okay. So they're gonna have, yeah, so everything from 0 to 127 you're just representing as usual with 8 bits. Just with not with a 2's complement, but just with a regular binary representation. And then you still have a bunch of spots left, like the things that would have been representing 128 through 255, but you instead use them to represent negative. Like and you have each negative integer is represented by the 2's complement of the corresponding positive
Right.
integer, meaning the 2's complement of the absolute value of the negative one. And yeah, and then that ends up being all the ones that have a 1 at the beginning. That's cool. So that means that like if you have 8 bits, you could, if you're just representing non-negative integers, you could represent everything from 0 to 255. If you want to do negative ones as well, then you can give then you split in half like the range of positive ones you can do. Like you give half of the binary representations to 0 through 127, and then you give the other half to the negatives.
Yeah. I guess the negatives do get +1 more value that they can represent, right? Yeah, because they can represent the
Oh yeah.
1 all the way to the left and all zeros to the right
Oh
of
yeah.
that.
Yeah, they do.
That's cool. Hmm.
Yeah. Although I guess the positives actually have the same number because they have like 1 through 127 as well as 0, so each of them gets 128.
You said they get 0 as well?
Uh, oh, actually, sorry, it was 0. I guess 0 isn't a positive number. I guess the non-negative ones.
Oh,
Uh,
wait. If it's all zeros, that is represented as well, isn't it?
yeah, yeah. So like the non-negative integers, those are 0 through 127. So you have 128 of those that can be represented. And then you have -1 through -128. So you have 128 negative numbers that can be represented as well.
Interesting. So you have, right, in that case, 127 positive integers, 128 negative ones, and 0.
Yeah.
Hmm. Why does the decimal form of the 2's complement for negative integers? Oh, it's only referring to the negative integers. So,
Yeah.
decimal form of 2's complement for negative integers. Isn't
Yeah.
this the same formula for the 2's complement for any integer?
Yeah. Yeah, it is. So there's like they're applying that definition and saying like we're going to take the two's complement of the absolute value of the negative integer, meaning like the two's
Ah,
complement of the positive version of it. So like for -1, that'll be represented by the two's complement of 1, and -2 will be represented with the two's complement of 2. And those two's complements happen to be the ones that like the spots that aren't already taken by the non-negative integers.
right. So the 2's complement of the absolute value of the negative integer is the absolute value of the negative integer not the 2's complement of the negative integer?
Uh, well, the absolute value of the negative integer is like the corresponding positive integer. So the absolute value of -1 is 1. The absolute value of -2 is 2. Um, so like so it's saying that like you take the two's complement of that absolute value. So the
What's the
representation of negative.
what's the
Yeah.
procedure of finding the absolute value of a negative number?
You just change the negative to a positive.
I mean, like in terms of the binary representation.
Oh. Uh. Hmm.
Clearly, it's not the 2's complement of the negative number, or else they would have mentioned that.
Yeah. Yeah. Well, it would be well, you got the binary. So if you already have the binary representation of the negative number, you can take the two's complement of the two's complement to get back to the absolute value of the negative number. Because like -1, that's represented as the two's complement of 1. And if you
Oh,
take the if you take the two's complement of the two's complement of 1, that gets you back to 1. So you can take the two's complement of the negative number to get back the absolute value or the corresponding positive number.
they seemed really like insistent on specifying that you're finding the 2's complement of the absolute value of the negative number. I guess that maybe that's closer to what you're doing.
Yeah. Well, this is kind of like the procedure like if you were starting with decimal representation and you wanted to find the binary representation,
Mm,
you have the negative number, then you take its absolute value, then you take the two's complement in binary notation.
I see.
Um, yeah, but if you wanted to like go the reverse direction, like you start with the binary representation of the negative number,
Right.
and you want to get the absolute value, then you would take the two's complement of the two's complement of the negative number.
Or you take the
Or sorry, you would take the two's complement of the negative number.
yeah,
Yeah, because that would itself be the two's complement of the two's complement of the absolute value.
yeah. Okay.
Yeah, that's cool.
Let's see. Computer addition and with negative integers. Here's an example of how 2's complement enables addition circuits to perform subtraction. Suppose you want to compute 72 minus 54. First, note that this is the same as 72 plus negative 54. In the 8-bit binary representation of 72 and negative 54, oh, okay, are 0, 1, 0, 0, 1, 0, 0, 0, and 1, 1, 0, 0, 1, 0, 1, 0, respectively. So if you add the 8-bit binary representations for both numbers, you get 1, 0, 0, 0, 1, 0, 0, 1, 0. I like the point here that 72 minus 54 is the same as 72 plus minus 54, or plus negative 54.
Yeah.
So since we can represent negatives as binary, I see the value of but it's like more difficult to represent the act of subtracting,
Yeah.
I guess, but it's easy enough to represent addition. So you can add negative numbers rather than subtracting. You just add the negative of the number if you want to do your addition in binary.
Yeah.
I wonder, what does subtracting look like in binary? I'm sure you can do it. I wonder if it's like significantly more difficult or something, so that
Yeah.
adding negatives is the way to go.
Yeah. Well, we actually did it last time, and it was
Yeah,
harder,
it
a lot harder
was.
than addition.
It was
Yeah.
not intuitive at all.
Yeah. Yeah. So it's nice to be able to represent it as addition. Yeah. So now I kind of appreciate like how two's complements can be useful.
True. I noticed this one here. I guess I wonder if it just. Oh, that's okay because we're adding. So you're gonna sometimes end up with a carry.
Yeah, but I wonder what this next part, if you truncate the leading one, you get 0, 0, 0, 1, 0, 0, 1, 0. This is the 8-bit binary representation for 18, which is the right answer. So I guess sometimes you get an extra one and you gotta get rid of just like get rid of it. I guess
Let's
I guess
see.
so.
So what were they trying to do? They were
Like
trying to
they're
do
trying to
72 minus 54. Okay.
yeah.
Oh,
Yeah, but they got an extra one there, which I guess they just get rid of it and then they just look at the last 8 digits and then it
okay.
works.
Interesting. Um, yeah, I wonder why that works.
Hmm. Yeah.
Like, maybe they'll explain that.
Yeah, maybe. Yeah, it has something to do with like the fact that like the one is what you would get if these were representations of ordinary. Like if these were ordinary binary representations, the one would be part of the answer. But like the fact that one of them is a two's complement somehow changes it,
Right.
and the fact that we're
The fact that
yeah
you're
something to do with that.
adding instead of subtracting the number as well.
Yeah, yeah, but yeah. Let's see what they say. So see, the description below explains how to use this method to add any two integers between negative 128 and 127. It is easily generalized to apply to 16-bit and 32-bit representations in order to add integers between about negative uh,
It's
2
million?
billion and 2 billion. Wow.
Billion. Okay.
Yeah. To add two integers in the range negative 128 through 127, whose sum is also in the range negative 128 through 127. So that's like a limit to it. You have to have both the numbers and the sum be in that range. Um, convert both integers to their 8-bit representations, representing negative integers by using the two's complements of their absolute values. Add the resulting integers using ordinary binary addition. truncate any leading 1 overflow that occurs in the 2 to the 8th position. Convert the result back to decimal form, interpreting 8-bit integers with leading zeros as non-negative and 8-bit integers as with leading ones as negative. Oh yeah, because that's because like in the representation, we have like all the ones that have leading ones are representing negative numbers, and all the ones with leading zeros are representing positive numbers.
Right. Hmm. Okay. So
Yeah,
let's see. The sum must be within the range.
yeah. Oh yeah, and by the way, it looks like they after this they do a long proof to show that this works.
Really? So I guess that makes sense that you'd only be able to get an answer within this range, assuming that we're restricted to using a consistent number of bits throughout the calculation.
Yeah.
Hmm. Okay. I wonder, does their proof explain um explain how?
Yeah, I think it should. It looks like it.
Let's see. To see why this result is true, consider 4 cases. 1, both integers are non-negative. 2, one integer is non-negative and the other is negative, and the absolute value of the non-negative integer is less than that of the negative one. 3, one integer is non-negative and the other is negative, and the absolute value of the negative integer is less than or equal to that of the non-negative one. And 4, both integers are negative. Case 1, both integers are non-negative. This case is easy because if 2 non-negative integers from 0 to 127 are written in their 8-bit representation, and if their sum is also in the range 0 through 127, then the 8-bit representation of their sum has a leading 0 and is therefore interpreted correctly as a non-negative integer. Let's see. With 8 bits, okay, you can represent 256.
Yeah, we can go all the way up to 255, but in the way we're doing it here,
Bind
like
only up to
yeah,
127.
yeah, only up to one, and then 128 and beyond are using these to represent negatives. So yeah, I guess this part is reasonable, I guess, like because you're specifying that the sum is also in the range 0 to 127, and you're just doing ordinary addition with binary representations. And if you're staying within that range, you're still going to have something with a leading a 0 in the 2 to the 7th spot.
Right. Cases 2 and 3 both involve adding a negative and a non-negative integer. To be concrete, let the non-negative integer be a and the negative integer be negative b. And suppose that a and negative b are in the range negative 128 through 127. The crucial observation is that adding the 8-bit representation of a and negative b is equivalent to computing a plus um, the 2's complement of negative. No.
That would be the 2's complement of b.
Right.
Yeah, because that's how they defined.
The negative is negative b. Yeah, that makes
Yeah,
sense. Let's see. Right, because the 8-bit representation of negative b is the binary representation of the 2's complement of b. Case 2, a is a non-negative and negative b is negative, and the absolute power of a is less than the absolute power of b. In this case, observe that I also wonder why they don't just say a and b. I see that
yeah,
it's like I don't know, it seems like more infallible logic to specify the absolute value.
yeah. I think they're just saying that because a is non-negative, so it equals its absolute value. Um, so negative b is negative, so is the
Ah,
absolute value of negative b. So since the absolute value of a is less than b, it follows that a is less than b. Because each of those is non-negative, so each of them equals their absolute value.
right. Hmm.
Yeah, and then a plus b in binary is represented as a plus the 2's complement of b, or a plus negative b is a plus the 2's complement of b, so a plus 2 to the 8th minus b, and then that can be rewritten 2 to the 8th minus b minus a, and that's because when you have a minus before stuff in parentheses, the minus applies to each of the things in parentheses. So minus b minus a, that's the same as saying minus b plus a.
Right.
So it's kind of just like a rearranging and regrouping of things.
Okay.
Um, so 2 to the 8th minus b minus a, and the binary representation of this number is the 8-bit representation of negative b minus a, which equals um, a plus negative b, again applying the negative to everything in the parentheses. Um, so, well, I guess, yeah, so we know that b is greater than a because a is less than b. So if you have a bigger positive number minus a smaller one, then you're going to get a positive number. So 2 to the 8th minus b minus a, that's the 2's complement of a positive number. Um, and we, huh, we, oh yeah, so I guess in any case, we want to make sure that 2 to the 8th minus b minus a is in the range we want. 2 to the 7th and 2 to the 8th. And why do we want that? Let's see. Because why do we know it's negative? Um,
I know they mentioned it only works if the sum is within the range of, in this case, negative 128 and 127.
yeah. Can you see what the a and the b were again? What are we calculating? See,
It
is,
looks like,
is this a minus b or what? Let's see, a or no, a plus b, a plus negative b. Oh, I think. Oh, we're calculating a plus negative b. Okay, and so we're calculating a plus negative b. We know that the absolute value of a is less than the absolute value of b, which means that the result is going to be negative. Because
right,
it's if we have a non-negative number and we're pretty much subtracting something that's has a greater absolute value, that's going to take us below 0. Because it's if you do 5 plus negative 7, that'll be negative 2, or 10 plus negative 100.
right.
Like uh So that's always going to, so we want to have a negative result. And we know that the result here is a plus 2 to the 8th minus b, which is 2 to the 8th minus b minus a. And that's a negative number, so the binary representation of this number is the 8-bit representation of. Oh yeah, because well, this is the 2's complement of b minus a, which means that it's the representation of negative b minus a by definition.
Right.
And now we need to make sure that this binary thing number is like we want. We want it to be between 2 to the 7th and 2 to the 8th, because it's representing a negative number. And it is because 2 to the 7th equals 2 to the 8th minus 2 to the 7th. Because like 256 equals or no, 128 equals 256 minus 128. And 2 to the 8th minus 2 to the 7th is less than or equal to 2 to the 8th minus b minus a, which is less than 2 to the 8th. And that's because 0 is less than b minus a, which is because b is greater than a, we saw. And b and a are both non-negative.
Right.
So that's why 0 is less than b minus a. And since a is positive, we're subtracting a positive. So b minus a is less than or equal, or we're subtracting a is non-negative. So we're subtracting a non-negative that can only make b less, or keep b the same if a is 0. So b minus a is less than or equal to b. And b is less than or equal to 128 because b is the absolute value of a negative number. And here we can only look at negative numbers with absolute value up to 128. And 128 equals 2 to the 7th. And so 2 to the 8th minus b minus a, since b minus a is less than or equal to 2 to the 8th, that means that oh no, b minus a is b minus a is less than or equal to 120 oh, so we're taking 2 to the 8th and subtracting from it something that's positive and less than or equal to 128. So that's giving you something less than 2 to the 8th.
Also, did you know 2 to the 8th minus 2 to the 7th is 2 to the 7th?
Yeah. Yeah, 256 minus 128 is 128.
Oh. So
Um,
there is some like relationship between the powers that can be accessed with just addition alone.
yeah. Yeah, in this case, it's because I think it's because we have, well, if you factor out the 2 on the right hand side, you have like oh no. Oh yeah. Well, if you factor out the 2 to the 7th on the right hand side, on the 2 to the 8th minus 2 to the 7th side,
Right.
you have 2 to the 7th times 2 to the 1st minus 2 to the 0. 2 to the 1st minus 2 to the 0 is 2 minus 1, which is 1. So you have 2 to the 7th times 1, which is 2 to the 7th.
And I think the relationship goes for all powers. Like 2 to the n is equal to 2 to the n plus 1 minus 2 to the n.
Yeah. Yeah, but I guess it doesn't work for like powers of 3, I think.
So like 2 to the 3 minus 2 to the 2 should get us
Oh,
2 to the 2 again.
Oh yeah, well it does work for like 2 raised to the power of 3, but if it were like 3 to the 8th minus 3 to the 7th, then I think it wouldn't work, because then if you factored out the 3 to the 7th, you would have like 3 to the 7th times 3 minus 1, which is 2. So like it kind of has to do with like you factor out the 2 to the 7th and you get a 1. Um,
So like 3 to the 3 squared minus 3 does not get you 3.
yeah, because then you have 9 minus 3, which is 6. Yeah, so I think it works for powers of 2, but not powers of 3.
Interesting.
Yeah. Uh, yeah, but yeah, I guess all that reasoning shows that like that big chain of equals and equalities and inequalities, you have 2 to the 7th on the left, less than or equal to 2 to the 8th minus b minus a is less than 2 to the 8th. So we showed that that shows that 2 to the 8th minus b minus a is in the desired range. And then they say, hence, in case the absolute value of a is less than the absolute value of b, which is the case we were looking at, adding the 8-bit representations of a and negative b gives the 8-bit representation of a plus negative b, because it's in the desired range, so we're going to get like we're able to have a representation because we've kind of arranged representations within that range. Yeah, and then they do an example and continue the proof after the example.
Let's see. On one hand, I think I need to review this, but on the other hand, I guess we could look at the entire proof first.
Yeah.
So, computing a plus negative b, where 0 is less than or equal to a, which is less than or equal to b, which is less than or equal to 128. Don't we need the sum? Oh,
Yeah. Yeah.
to be.
Well.
Go ahead.
Yeah. We're gonna do like in the example we have like
Oh,
39 plus negative 89. So we'll be doing a sum.
okay. A plus negative b, where a is less than b, and b is less than or equal to 128, but neither
Yeah.
a or b is negative, right?
Yeah. They're both positive. But we have negative b, so then that's how a negative one comes in there.
Right.
Yeah. So it's kind of like an example of something within the range that was being discussed in the previous part of the proof.
Right.
Yeah, so 39 plus negative 89, well, we got to do the binary representations of each of them and add those representations. So first we got to get the binary representation of 39, which is done in the usual way without 2's complements.
Right. Let's see. So we have 8 bits. We need the 32. So that is and then we need 7 more. So we need the 6 and the 1. There's 7 more. I guess we would need a 4, a 2, and a 1.
Yeah.
Plus 89. So we can find 89 and then find the 2's complement of it. 89, we can get 64 from here. Let's see. So we have 25 left. We can get 16 and 9. 16, and then with 9 we can do it this way. The 2's complement of 89.
Yeah.
If I did 89 correctly here.
Yeah, I think so. Let me double check. Yeah. Yeah. Yeah, looks good. So yeah, taking the 2's complement, you'll flip the bits.
And then add 1.
Yeah. Yeah. And yeah, so now we have the binary representations of both the numbers, and then now we just got to add them.
Okay.
So we'll add do the binary representation of 39 plus the binary representation of 89.
So let's see. I got this.
Yeah, I think that's right.
Wait a second.
Or wait. Oh, actually, so in the first column, so you're right that there's a 0, but then you got to carry a 1 into the second column. Second column from the right.
True.
Yeah, yeah. So whenever you get 1 0 in a column, you put the 0 in the column and then carry the 1 to the next column. Yeah, so then in the second column, you'll have 1 plus 1 plus 1, which will be, they'll give you a 1, and I guess they'll carry another 1. And then, yeah, 1 plus 1 plus 1 again, carry a 1. And then you'll have 1 plus 0 plus 0, carry, and then you'll have 1. And then in the third column from the left, yeah, 1 plus 1, you'll have 0 and then carry a 1.
Let's see. Now I see well, I mean, since we're doing so much binary addition, I definitely see the use of having a map like they mentioned. Wait, is this?
Oh, wait, actually, I guess, let me see, one thing must, oh, wait. I think, in the, Oh yeah, so in the third column of the addition, you have 1 plus 1, so that'll give you a 0 in that column, the third column from the right.
Let's see. Where?
The third column from the oh sorry, the third column from the left of the addition, where you have two
Oh,
ones.
this will get you a 0.
Yeah. 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 I think yeah, I just double checked it and that's right.
Hmm.
Yeah. So now we just got to find the decimal equivalent of that.
Okay. So we have.
Um, but so this is like so we see that like we got a leading one like and the rule is like if you have a leading 0, this is the representation of a positive integer. If you have a leading 1, it's the representation of a negative integer. So it's the representation of a negative integer, um, and uh, so which means that this is really the representation of the 2's complement of the negative integer's absolute value. So to find what the original integer was, we got to take the 2's complement of that and then put a negative on. So that 11001110, we got to take the 2's complement of it.
To find the what?
Oh, we gotta take the 2's. So like yeah, like we you did the addition, and it got 11001110. So that's like that's the answer to the addition. What it represents, because the rule is like if something begins with a 0, then it represents a positive integer. If it begins with a 1, it represents a negative integer. So this one begins with a 1, so we know it represents a negative integer. Um, but we can't just like convert right from that to decimal, because the representations of negative integers are like are 2's complements. So
Interesting.
we need to convert back to the original integer. um, and so this representation is the 2's complement of the negative integer's absolute value. So to recover or like to get back the negative integer's absolute value, we got to take the 2's complement of this.
So do we drop the leftmost digit when we're taking the 2's complement of a negative number?
Uh, we don't have to, because only drop the leftmost digit if it goes beyond the 8-bit limit.
Oh, true.
Yeah, so we can keep the leftmost digit, but and just convert all the zeros to ones and the ones to zeros,
So we would end up with first,
and then add one.
right, the 1's complement. Then we get this.
Yeah, and then yeah, uh,
So that actually equals.
yeah, yeah. So then we can calculate that, and whatever that is, that's going to be the absolute value of the negative number. And then we'll just put a negative onto that.
Is this negative 50?
Yeah, yeah, exactly.
Interesting. So you really can't just go from the negative binary representation to the positive by dropping the leftmost digit.
Yeah, yeah. It's like you only drop the leftmost digit if you have that overflow. If they have like a 1 in the 2 to the 8th place, then
Right.
like a ninth digit.
Huh. Let's see. I want to pick up on these cases next time.
Yeah. Yeah, that sounds good. Yeah, we can do cases 3 and 4. And then after that, they'll do hexadecimal notation.
Nice, nice.
Yeah, and that'll be more straightforward, I think, because that'll be kind of like just like a similar idea, but with 16 digits.
Right. Hmm. Yeah, maybe a little less memorization, perhaps. I guess we'll
Yeah,
see.
yeah,
All right. In any case, we'll do that Tuesday.
yeah.